Yeah, that's President. Right. Our next speaker is Konstantin Wernli.
Okay, so welcome everybody to the last lecture. It's a nice series. So the title of my mini course was Locality and Globalization in Perturbative quantum field theory, and probably more appropriate title would have been Locality or Globalization, maybe Locality or Globalization. It turns out we didn't. I think we're not quite going to get to locality, so I decided to today talk a little bit globalization. Needs a little less machinery. But first, let me start doing a recap of the series so far, and then also sort of maybe shift our view a little bit towards the big picture. So in German, we have the saying that sometimes you don't see the forest for all the trees. And we all know that in math there are a lot of trees, right? And like every tree has a lot of leaves, and the leaves have insects on them. And sometimes it's good to take your drone and look at the forest from above. So I also want to sort of give a schematic overview of what I think of this perturbative 3D quantization. So in the first lecture, I sort of explained what I understand under a classical field theory. And so for me, maybe this is kind of ideological. This is really a starting point for the most of my considerations. And so this classical field theory, in some sense, is equivalent to the PDE describing the space of solutions of equations of motions, or we call it SOL, I call it EL, and in many cases, critical locus of action function, right? So this is some important capture field theory. Then in the next lecture, we sort of looked how to associate to this classical PV theory. So I didn't tell you how to get to the how to actually, if you start with this goal to a BV package that extends it, okay, but I told you that what is a BV package and what is a classical field theory recovers, and there's some arrow going this way. And that is sort of equivalent to what in the Costello volume book is called local and infinity algebra. I mean, in something. It's a local and infinity algebra. It has more Cartan set, or I also call it sort of curly EL. Here, so it's M together with some alterations. Right, and then kind of important for me is that for any point in here, so I mean like point in degree 0, so it's actually point in here, then I get this family of twisted and infinity operations. Okay, so. And that describes sort of, if you want, that describes the neighborhood of this point in the Wernli space. Some version of formal moduli problem, so it has words, maybe. And then the next lecture, finally, if you have this, okay, there's some more things there, I'm putting a little bit under the rug, then you can go and compute the perturbative division function. Okay, and so also I want to say that kind of I want to connect with functorial field theory, which is why I sort of care about partition functions. In some sense, on the side remark, so this expectation value of 1, okay, observable, which is constant from the 1, and you could also, I mean, if you want, you could compute expectation values of other observables. There's nothing stopping you from doing that.
Asking what A.
Yeah, so A was an so this partition function depends on this point in EL, right? In Euler-Lagrange space, and A is an element in the cohomology of L1 twisted by that X0. So to compute it, you need this choice of a strong deformation retract, or if you want PK triple, or whatever you want to call it. So, and then, yeah, so this guy here, it depends on this choice. And sometimes you want to make sense of this functional interval here. So you get integrating over in K and then the exponential of the action function with A that's I of A plus phi. Okay, so maybe I should sort of explain my notation again. So you have M, and then if I pick some x0, there's cohomology of L1 twisted by x0. And then this IPK triple is maps right like this. So chain maps, quasi-isomorphisms from Fn to the cohomology, and the choice of a retraction is here. Here I'm also sort of putting some ominous new that I don't want to talk about too much. And the important thing about this perturbative partition function is that it's one way to write it is a product of three factors. So C0, C1, bigger equal to the zero rule, only more than 2. So we have different degree of control over those three pieces. So C0, well, that guy is perfectly fine. So he just consists of evaluating the reaction function of x0, and then generating function for this induced infinity structure on topology. We have some LIX0, and then I wrote time. Tutorial here. So this one we have perfect control over, and it's actually already interesting gadget, right? And then the C1, that's in some sense is the most mysterious guy, because it involves taking like a regularization of L1. So L1 is quadratic term in your action function restricted to image of K. We want it to be something like e to the I pi over 4, signature of L1, x0 restricted to image of K. Of course, this thing is usually still infinite dimensional. It's not really clear what this should mean. Same thing is true for the denominator, which is superdeterminant. L1 x0 restricted to in K, and then actually you want to multiply it with okay, half density on the cohomology. So should be in the square root of the determinant line of this cohomology. Okay. And so here what I'm going to say is that when you do BV, you take twice as many variables as you should have. So now instead of a density, you take a half density, and then 2 times 1/2 is 1. I mean, density. Densities are what you like. Okay, so let's not maybe dwell more on the subject right now because it's in general really pretty
But we are
mysterious.
changing the sports, it was
Yeah.
hard to read the top line from the one.
So finally, this C big or equal than 2. So that's where you will have like your series of Feynman diagrams. One way to write it is that you take H bar to the negative order characteristic of gamma, some overall gamma, and divide by automorphism group of gamma, and then evaluate these graphs. Okay. And so in general, it's kind of hard to write down what it is, but we will study it today in an example. Okay. And here you have a different problem. So here the problem is that usually your Feynman rules that describe this thing, they diverge, and then you need to do renormalization. So what this thing gives you, but if you kind of manage to do that, what this thing gives you is invariance of your underlying space-time manifold, or if you want, it gives you a loop enhanced homotopy transfer. So two different viewpoints on this kind of gadget. Z0, I just see sort of Z0. I can see the use other chalk. I have some. Here you just see the homotopy transfer. So this C1 in some mysterious way, okay, so in general, you want it to be something like half densities on the Euler Lagrange modular space. Whatever that is, so that's a complicated object. It's typically singular, so maybe. Yeah. So I don't think that it's really clear in general what this object should be. And here you finally will get some invariance of M, or if you want this loop enhanced homotopy transfer. And now, let me just say what this gadget is supposed to satisfy. So, if you remember in Paolo's class, there was this quantum BV operator or BV Laplacian that was acting in the space of fields. So in general, kind of on the space of fields, it needs to be renormalized because I would just say we have a formal BV Laplacian, something like that. One that it annihilates the actual functional. That implies the quantum master equation. And then what we expect from this, so in finite dimensions, if it was a real BV Laplacian, we would have a theorem, but because we sort of this is an infinite dimensional space, this Laplacian is not really defined. What we expect is that this perturbative partition function also satisfies quantum master equation. We expect that it's gadget see perturbative x0 a. So what do we expect? We expect that it satisfies the QME on cohomology somehow. So cohomology has its own BV Laplacian because it's also an odd symplectic space, and it should be closed with respect to this BV Laplacian. So delta, let me call it H, and also like suppress some of the decorations. So we want this to be true. And okay, we made some choice here. So we picked this standard deformation retract. So we want that under deformations of this, under deformations of this G, that Z changes by an inexact term. Okay. d by dt, phi of gt is part of something. Okay? And that is what gives us invariance here, right? Because we made some choice in defining this thing. And so we want to say that it's independent of these choices. Well, the way in which it's independent of these choices is that the DV cohomology class of this person is expected to be independent of these choices. Now, for a general field theory, sorry, you have a question?
Yeah, sorry,
Yeah.
where did T enter the game?
T, I'm just picking like some family of G's there. So, should say for GT family of SDRs parameterized by some. In general, this is just a program, right? You start with kind of innocent looking classical field theory, and then, yeah, has to undergo all these kind of funny operations. And so this kind of step, this first step here, that's sort of relatively well understood. So whenever you have a classical field theory, you can build such a gadget. Okay, then let's not dwell too much on that. But then this arrow, this is okay, quantization, and we all know that this quantization is always very problematic, right? For here, there's just a million problems. But today I want to kind of discuss an example where we have some understanding, and that's transition theory. Then for this example, also kind of give partial answers and some conjectures about the question, what kind of object does this thing define on the modular space? Because what we did now is that for every point in the modular space, I'm defining something. And so it's a question like, what kind of family does this thing, what kind of global object do we get on this Euler-Lagrange modular space? Okay. So for Chern-Simons, we have some partial answers and some conjectures. I'll go to present you today. Sergei's terminology problems. Any more questions before we start with that? So just let me recall that yeah, in Chern-Simons theory, we have like M is a free manifold and space of fields. Okay, we pick a principal G bundle, but we think it's trivial. So G is a V algebra, so it's quadratic. It means it has an invariant bilinear form, and also we want it to be unimodular for the same reason that it had to be unimodular in all its talks. Space of fields is just an action from the trivial principal G bundle, and the action functional is Chern-Simons is action functional 1/2 A plus 1/6 A. Space is a space of flat connections, so those A which satisfy that curvature is 0. So that was the sort of step 1 for classical Chern-Simons theory. Now, before I go on, just to kind of embed it in this cartoon that Sergei was drawing. So, yeah, so there's a unit disk. Maybe let's focus on the upper hat disk. So there's this invariant C hat of Q. It's defined inside. And then at roots of unity, there's this WRT of K, right? Okay. And now all that I'm doing is that I'm looking at this point here. Okay, so as Q goes to 1 or K goes to I'm considering this object here, which we think that it should be somehow asymptotics of this gadget as Q goes to 1 or K. But so maybe in similar spirit to Sergei, you can see that, okay, this guy depends on some x0, right? So it's some reference flat connection, either WRT or this guy depend on a flat connection. So yeah, even if we consider asymptotics of this guy, we have to get rid of this flat connection. And the way to do that is to average over it. Only that averaging over moduli space of flat connections is maybe a bit tricky in general. And so we are not quite there yet. Okay, so BV extension of this guy. So simple. Natural assignments is one of those theories where you can just magically make all of your letters early and then it's your BV theories. Maybe a short anecdote from my PhD. So I know that my PhD, when I started, there was a collection of problems, and one of them is work on gravity, one of them was assignments. I didn't have any idea, picture assignments. Turned out I was lucky because, yeah, in assignments, if you want to find the BV theory, you just make your letters curly. In gravity, if you find the BV theory, you pick some A3 paper, you go to a room for 2 weeks, and then you emerge, and you go back because you made a mistake. Gravity is more complicated. We're just also kind of trying to advertise that this is really very cool, and here it's so simple. Okay, so you just take inhomogeneous differential forms, you plug them into your actual functional, that's it. Okay, so L1 is just the round differential, L2 is in brackets, and needed over branch space. It's just space of connections. Okay. Are so good. And okay, so here we kind of, yeah, similar to Paolo's lectures. So this fraction functional satisfies this classical master equation. It's equivalent to the fact that d squared equals to 0. We have Leibniz identity about d in bracket, and bracket satisfies type B. Then on the master equation, that's equivalent to formal quantum master equation. It's equivalent to unimodularity. This meant that trace of add x is 0 for all signs. Okay, so now we sort of have the classical BV theory. Now, next step is to go to the quantization. Okay, so we take some reference flat connection A0. And then we have the twisted infinity operations. So they are just L1 of A0. Well, that's just a twisted around differential because it was just L1 plus L2 of A0 and blah, and actually L2 of A0, that's just the same. Okay, so it just remains the. In this case, there's nothing to twist here.
So in this case, you're fixing a connection, an honest to God connection. Obviously.
Yes, yeah, now I'm just fixing honest to God that connection and twisting the around differential with it. Yes.
What does the curly?
Sorry?
What does the curly mean?
Curly A. Yeah, so curly A here Yeah, it's some inhomogeneous differential form with coefficients in the algebra. You can read it because you sit right here. Okay. And now, next step is we need to find our contracting triple, strong deformation retract. So it turns out in this case, there's a nice one given by any Riemannian metric. So take Riemannian metric G. Sorry, M. The metric is called G. Okay. Then we get sort of Hodge decomposition, and with it a strong deformation retract of algebra of differential forms. Here you take cohomology of twisted differential. You can include it. Yeah, I think I need more space actually. Let me continue over here. So maybe, yeah, I have some space here. So maybe let's add some more details. Okay, so if I have Riemannian metric G, then I get code differential. And then I have a Laplacian, which is just anti-commutator of differential and codifferential. This is a nice elliptic operator, and its kernel is called the set of harmonic forms. I'm noting everything with index A0. Okay. And then the Riemannian metric also gives me orthogonal projections from round forms to harmonic forms. And, this is an important theorem in geometry that yeah, the harmonic forms, they're isomorphic to homology. Okay, so maybe trying to abbreviate a little bit my notation, but maybe it's clear. So here you have PA0, here you have Hodge isomorphism. That's given just by taking some harmonic form chi, sending it to its cohomology class. And here I have inclusion, right? So harmonic forms in particular, just regular forms, so I can include them. I something phi maybe. I is just this inclusion composed with phi inverse, and P is phi equals with PA0. Okay, and finally, I need to tell you what K is. So K is codifferential composed with inverse of this operator. Okay, so this operator has a kernel, so it's not invertible. But somehow what I'm doing is that I'm just on this kernel, I'm adding the identity. And then it becomes invertible. Okay. Invert it, compose it with this. And so this is a chain homotopy. Remind. And it's good exercise to verify that it's a strong deformation. Yeah.
For I, you got I was iota. Where did the iota come from?
Yeah, iota is the inclusion of harmonic forms into
Oh, okay.
into all forms. All right. And so, because we're on a free manifold, this space of harmonic forms actually carries natural -1 shifted symplectic structure. So let's see. So it's just induced by Poincaré pairing. Okay, so
You can shift the harmonic things down first.
yes, so one forms at degree 0, and so two harmonic forms, and we just send them to integral over n. They need to take pairing because they're the algebra values.
Technically, but it's probably concerns operators K
Yes.
to the Laplacian A naught. So we care about isolated versus not isolated A0 because they'll behave very differently, right?
Yes, but so I'm not assuming that A0 is
So that's an assumption.
no, I'm not assuming that. So
Yeah.
So delta is allowed to have a kernel which is harmonic forms. So those are infinite. So in particular, there can be harmonic one forms, which correspond to infinitesimal informations of this. In fact, I'm hoping I will get there, but I'll say something about that in a bit. Okay, so and this PV Laplacian has some actually rather explicit formula. So if you have somebody in this cohomology group, then you can decompose them into form degrees. Right? So this is inhomogeneous differential form. So here you will have some from 0 to 3. And then you can express this in the basis of harmonic forms, and then there are some coordinates. J. And then so here I is the degree of this harmonic form, and then there are J of those in degree I. So here J goes from 1 to I at D. Okay. Forms I. And then PV Laplacian on harmonic forms. Okay, it's just some signs. And then here I'm taking derivative with respect to A0, A3. So how I'm writing plus minus d by t 1 j d by d 2j. Okay, that's because the A0 and A3 coordinates, they are canonically conjugate to each other, and A1 and A2 coordinates are also conjugate. Oh, yes? That's superscript I. Yeah. So my indices and superscripts, they're also all quantum, so they're deliberately in a superposition of several indices. It's not possible to measure it. Yes, arbitrary precision. Okay, so now I'm after this kind of introduction to Hodge decomposition, I'm going to tell you what C0, C1, and C2 are. And in this, for this theory, we can all write them down explicitly. Okay. So, okay, so for C0, it's just the same, right? So, you just have Chern-Simons invariance of E0, and then you get these kind of higher infinity operations. Factorial, and then 0 prime, sorry, here it's A, 0 A's, and A's. So C1 is more interesting. So C1, here it's actually possible for this differential restricted to the image of K. So image of K are co-exact forms. And so now there is some sort of nice and long computation how you can make sense of both the signature of that guy and the superdeterminant. And it turns out that superdeterminant somehow assembles into analytic torsion. And signature is some even more, I don't know, it's another kind of subtle invariant, so it's beta invariant of that local system in G. So maybe let me explain what this person here is. On this one, okay, maybe for another day. So analytic torsion, one way to define it is through the weird combination of determinants, regularized determinants of Hodge-Devan Laplacian. So you have this Laplacian on all P forms, right? Yes?
Sorry, finish what you were saying first.
Yes, okay, so it does have a kernel, but then you're sort of restricting it to like the orthogonal complement of the kernel. You're taking the determinant, and then raising that to some weird power, namely minus P to the minus 1 over P divided by 2. And then you have to, so if there was no cohomology of A0, that would be all of it. But now, since there is cohomology, you have to multiply this with some, So the square root of the generator of the determinant of that cohomology line. Okay, and that's what is called the analytic torsion.
You say again what the mu is?
Yes, so I picked some basis for my cohomology, so then I can just write mu. It's just taking the product of all of those guys. So that's the element in the determinant line, right? So it's a big wedge product with I and J, and then I'm taking square root of that. Sorry, no square root here. No, not in the analytic torsion. The square root is only. So if you want to know more about this, I mean, one nice place to read about this is Pablo's lecture notes on torsions. That's so. Or there is also a book by Turar from torsions. So yes.
Question, just I think you probably said this already.
Yes.
But when we do these one loop corrections,
Yeah.
you're not getting that formula directly out of the Lyman A.
No.
You're using this as input to your construction of this picture.
Yes, so there was kind of one person like Z1 that was floating around on the board, and it was supposed to be regularization of exponential of signature divided by superdeterminant. So now I'm choosing regularization of signature and the superdeterminant. So regularization of signature is this, and regularization of superdeterminant is this. Okay. Yeah.
It looks like you're raising the determinant of the BV Laplacian some power, but I can.
No, now it's no longer BV Laplacian.
Oh,
This is a Hodge-Devan Laplacian.
so what's this? The determinant? It looks like there's a negative P, -1 over 2.
Yes, there's negative P and then -1 to the P and then divided by 2.
Minus P -1 over 2.
Yeah. So this is of course a quantity which a priori strongly depends on the Riemannian metric, right? So there's a big theorem called Cheever-Müller theorem that is actually topological invariant.
Should be probably determined as prime.
Yeah, so I think I said it, but yeah. We can put more decorations, but it's also see the regular rise.
Yeah, and also maybe another point is that, well, it sounds like if you change the basis in homology, then this sort of mu will change. So probably to have something that makes sense, you need to fix guys in a way compatible with magic.
Yeah, I'm fixing maybe orthonormal.
Okay.
They're raising the Laplacian to the top.
Yes, I'm raising the determinant of the Laplacian. Oh, it's a little, I mean, okay, you have some Laplacian. Well, it's an operator with a kernel. You're throwing away the kernel. You end up with the invertible operator. You define the it's a series, well, zeta regularization. It's long stuff. Yeah, sorry.
Maybe a quicker question.
Yes.
So we're calling this analytic torsion. Is
Yes.
there like a class of three manifolds for which it's like just one?
Good question. So, I'm really weak on three manifold topology, and there's a class where this is one.
Yes. I know, no, for three manifolds, no. Yes. I think it's sort of one for even dimensional manifolds automatically.
Yeah, and for one, yeah, for even dimensional manifolds.
What is it for three torus? Your function on character, right?
It's not a number, it's a torsion.
It's a function, yeah.
It's an element of the determinant lines, right?
So it's a collection of numbers.
But it's probably some simple object, right?
Yes.
What do we know what the simple answer is?
Oh, it's itemized torsion. I don't know.
What is a function on, yeah, or section of this line path?
So. No, I don't remember.
All right, so, yeah,
I confess, I can't quite read the top line.
yes,
So the sum, what is that running over?
over n. Right,
Okay, and then what follows that? 1/n?
Then it's 1 over n factorial, and then you're integrating over m, the pairing of the cohomology class A with the induced and the operation applied to the copies of A.
And then I think you haven't closed your pairing bracket, eh?
No, that's not true.
Okay.
Thank you. Okay. So, let me breeze through this definition of C2. So we have time to talk about something interesting. Let me write again. So, okay, some series of Feynman diagrams. And here now, I'll just tell you in two examples what they are. Okay, so my favorite graph is theta graph. So how would you evaluate this guy? So how would you define f of gamma, right? So well, to every each edge you associate a differential form kappa, and this kappa is the integral kernel of k, x0. So this means that if you to apply k to omega, you take kappa and redshift with omega. That depends on two variables. Just kappa is in two form on two copies of M. With values in G and in G. And it has the property that it's the integral kernel of this chain. Okay. And okay, then there's also a little simpler object is F, which is just totally anti-symmetric tensor induced by Lie bracket multi-pairing. And so then to write the weight of this graph, you just integrate over your manifold. So now I'm expanding these two guys in the basis of the V algebra. Then what? So I'm getting kappa. L kappa to M. And as I case. Right. Okay, so if every edge you get kappa, and for every vertex you get F. So this one type of graphs, and then there's also a graph with leaves that are labeled by A. Okay. And so let me just write schematically what it is. So here you're getting something like integral. Again, you're integrating over those 2 points. And then so you're placing A at the first point, A at the second point. Then there are 2 Fs and 2 kappas. Okay. And fill out the indices if you want. Okay, so that was definition of C2. And now what about this property that it's closed under the Laplacian? Well, that is another theorem of Catania-Munoz. So around 0.8. Okay, so they say that this delta 0.2 is right. Yeah, actually, so did you prove it for non-trivial flat connection?
Well, I think that all that paper was zero connection, but sort of, yeah,
I mean, it's kind of similar arguments, right? I mean, it's kind of the same argument for
the same
non-trivial flat connections. So you also have some lecture notes where, yeah, I wrote for all of them. So interestingly, in this case, if you vary the metric, okay, so you get something delta exact plus something which is not delta exact. So here you have some anomaly. That's some interesting part about transassignments. So here you, this is called framing anomaly. You kind of have to deal with that. And then there is sort of result that you can multiply. So there is some Z prime, which is by Z prime H power. Gravitational transassignments action. So here you can sort of, so this gadget is what? So you introduce a framing of your free manifolds. So that's a realization of the tangent bundle. And then using that, you can define transassignments invariant of the Levi-Civita connection of G. Well, there is a framing anomaly, but you can cancel it. Yes. And okay. So maybe in the last 10 minutes, I think this is all kind of old stuff, but maybe in the last 10 minutes, let me tell you a little bit what happens when we're trying to deform this easier. Okay. now let's look at this A flat. So that's the space of all flat connections. And now here is our reference point A0. And now let's assume we have some curve of flat connections, AT.
Well, this is a generic point. This is not the trivial topological
No,
connection.
yes, it's a generic one. Curve of flat connections. So what does it mean? So if you take the derivative of this guy and e equals to 0, then you can see that the tangent vector must be dA0 closed, right? So all the curvatures are 0. So in particular, if I take derivative, it will also be 0. But you can compute this derivative and it's just twisted around in front of this. Now, okay, so let's turn this problem around. So let's say I have some alpha, which is closed, right? So it's a closed one form. And I want to lift it to a curve of flat connections. Okay? So the first guess would be you just start with A0. Let me call this A1 of t. So you just add t times alpha. Okay. Now you can compute the curvature of this guy. Well, you will get curvature of A0. So that's 0 because A0 was flat. Then you will get t times the round differential of A alpha. Well, that's 0 because this guy was closed. And then you get t squared over 2 times alpha bracket itself. Okay. And of course, like that is not 0 in general. And now we need to so this is kind of deformation theory exercise. So now we want to lift this first order deformation to a second order deformation. So we want to add something that when you take the curvature, it cancels itself here. Okay. So let's define some A2 of t. And now let me call my alpha alpha1, and I'm introducing some alpha2. And I want to see what's the condition on this alpha2 so that that term vanishes. And okay, so it turns out that you want a round differential of alpha2 is exactly this bracket here. Okay. And so now you can see that this bracket here, I mean, it has no reason. So this is saying that this bracket should be exact, but a priori, this bracket doesn't need to be exact. Now we go way back to when I talked about smooth points in this Lagrange local. So I said that the point is smooth if all induced at infinity operations vanish. And so here you can see that, I mean, this guy is exact. Okay, so it defines some cohomology class. Sorry, it's closed, so it defines some cohomology class. But we need this cohomology class to be 0. But if L2, so L2 is just taking cohomology class composed with pairing. So if that vanishes identically, then this will be 0 in cohomology, and we can solve this problem for any alpha 1. And so that's actually a nice exercise to think about because I'm a little bit short on time. I won't go into details. It turns out that if you continue playing this game, so if all L infinity operations vanish, you can take any closed one form and lift it to a curve of flat connections. Something like A infinity, which is A0, and then this element here is just sum over trees. So here we have a, so sorry, I wanted to say that if this guy is in fact exact, then we know how to find alpha 2 because we have our chain homotopy. So alpha 2, that's just Ka0 of alpha alpha, and let me just write this as a tree. So it's you can represent this as a tree where you plug in alpha alpha, and then you have K. And so if you play this game all the way, then you will see that you're just ending up summing over all possible trees. So let me say. Okay, so this is some sort of Feynman diagram evaluation. And in fact, so now the observation is that those are precisely the same trees as the ones that appear in the perturbative partition function. Okay. So in Z, you have diagrams of the form, there's enclosed diagrams, and then they have some trees going up. Okay. So those trees are they're exactly the same trees as the ones that go into this deformation problem. So yeah, so that is actually the same. Let me give this guy here a name. So, and let me just call it tau. Right now. So this is the same as plugging in taus here everywhere. And of course, like these trees could also be in other edges and so on. And so now if you sum over all possible insertions of these taus, well, so here you have k's, right? So then it turns out that what you get is actually just another k for that connection that you get if you do this game all the way to infinity. Okay. So here, let's call this guy k. This is actually just sum k raised to 0. Now I'm plugging in tau here everywhere, k times, and k is in between. And so this is chain homotopy for A1, okay? And so A1 was the element that I got from A0 by lifting the going time one along the curve defined by this tangent vector. And so long story short, so there's kind of, this is proof of kind of small theorem, namely that if you take this Z that I was explaining, and you evaluate it at A0 and some alpha. Now I'm just taking alpha, which is a closed one form. So that's C of A1. With this kind of, maybe I already used prime. So let me just give it a name. So here's the gauge fixing. It's this guy, but for a different gauge fix. Okay. So here I follow my curve, A1. And now the point is, if I computed this perturbative partition function A0, I can sort of go and transfer it over to this other flat connection. So actually, kind of, there is in the radius of convergence of this map, there's sort of a well-defined global object. Okay. Now, unfortunately, okay, this is very nice, but it all only lives kind of in a neighborhood where this map converges. And there it's sort of not unique because I could have started from any point in this neighborhood. I could have started with any flat connection in this neighborhood. And if you do that, it turns out that the corresponding Z's, they just differ by gauge transformation. Okay. So now the conjecture is that all these guys, they assemble into something that's defined on the whole moduli space. That is not gauge invariant, because, okay, if you sort of change the reference point, there will be some gauge transformation, but up to, it's gauge invariant up to sort of global BV exact terms, okay? So, these patch together to a global V, use BV cohomology class. Is well defined. Okay, I think my time is almost up, but just let me sort of state the corollary. So the corollary is that, yeah, so when we integrate things, we only care about the cohomology class really. So that if we have a corollary is that if we have a closed smooth component of the modular space, smooth component L, yeah, then we can integrate. So that's a corollary of this conjecture. Okay, so it's not a corollary of the theorem. Then the integral of C over Shem is well defined. So it doesn't depend on any of the choices that we made in this process. Okay, so we choose a gauge fixing and we choose a couple of B0 as the centers for our open sets. But in the end, we end up with this. And okay, then the conjecture is that this guy here, that's precisely what appears sort of in the asymptotics of WRT invariance as a contribution of that component of the modular space. So yeah, stop here.
Questions, comments?
Yes,
For this conjecture, a priori might agree that there's monochrome issues, right? With like
yeah,
producing sort of a line bundle maybe over early M, locally producing a section, which you may not be able to patch together globally in a section.
yeah.
And those can be sort of like really interesting. Do you have any sense of like why you think those vanish?
Yeah, so there is another global object, which is that you just take all flat connections on that component, and for every flat connection, you use the same gauge fixing that we had initially. That's the one used by Riemannian metric. So you see here, it's kind of a little bit annoying point. So I start with some connection A0, which has a nice Riemannian metric gauge fixing. But then when I start deforming it, in this procedure, I end up with another propagator that's no longer induced from the Riemannian metric. As a matter of fact, it just, when you know what this means, it uses the gauge fixing operator D star A0 instead of D star A1. But still, it's sort of, that object is kind of globally defined. Just taking D star kind of A0 everywhere. We saw the idea is still that that gives you something that's sort of that transforms in the BV exact way under gauge transformations. Sorry, there was no question. Yeah.
Yeah, sort of main question, just when it comes to just quotient, how I gauge the difference for from the quotient stack.
Yeah, that was what I'm trying to do in the end, right? But still, the quotient stack is sort of non-trivial.
Would you mind repeating the question?
Yeah, so the question was, why don't I just quotient by gauge symmetries and work with the quotient stack? So in the end, that's what I want to do, but quotient stack still sort of has some direction, right? And let's just say it's a smooth case of this quotient stack can have be three-dimensional manifold or something. I still need to integrate over that. There was Leon first.
My question is basically, I mean, this seems to come from the particular gauge fixing that you choose, right? It's very specific. You need to choose a Riemannian metric. And you say, hey, my background connection is Levi-Civita, if I got that correctly.
No, that's just the one thing that cancels the framing. It's kind of separate story, actually.
But so
Yeah,
could it be just like an anomaly due to the specific gauge fixing you choose?
So framing anomaly, that's due to the cage fix. So framing anomaly is sort of another story. It's kind of doesn't really talk to globalization that much, as far as I know. So here I'm just, I mean, Riemannian metric is just useful because it gives me gauge fixing for every point in the modular space. But I think because, you know, the kind of generalities of homological perturbation theory, even if you just start with gauge fixing at one particular point in your modular space, I mean, using these techniques, you can transport it at least in a small neighborhood where things converge. If they do. I mean, in this case, things actually converge because things are nice. Yes.
Can we extend Z to some differential form on the modular space of flat connection?
Yeah, thank you. So, so here I was kind of, I'm sort of running a bit to get to here. So I was pretty precise, but so here this is kind of PV modular space and C is a half density. Okay. But then there's this this isomorphism, at least if you're on a smooth component, there's an isomorphism between half densities on the V modular space and densities on the Lagrangian side. And so you could imagine that, you know, maybe this M just looks like a shifted potential bundle of some nice component of your modular space, some fixed index. And then this Z would indeed define sort of volume form. This volume form is not globally well defined, but its cohomology class is well defined.
What I mean is we can add the ground differential of the modular space of flat connection to the master equation. So
Yes.
yeah.
Yeah, you can also do that. Yeah.
Okay.
Then it's kind of you will get some differential form valued in densities in modular space. So,
Yeah, I'm wondering if we can fix the global gauge in this way.
yeah, good question.
Yes. What in my mind is some global gauge fixing such that we do not need to care about any gauge transformation.
Yeah, I don't understand what you mean. Maybe let's discuss later. Sorry.
Okay.
All right, yeah, let's proceed to lunch or whatever you guys do during this break time. And our next talk will be at 2. The same Konstantin.
Most, we didn't understand you.
What I mean